Okay, so in lesson 11.8, what we're actually going to be doing is modeling the data we looked at in 11.7. Sorry about that. So we're going to be modeling the data that we looked at in 11.7. So just as we were doing before, we're going to look for those finite differences, but now we're going to do something with that information to actually write an equation, to model an equation. So in 11.7, we saw how to determine whether the polynomial actually exists with degree 5 or less, basically. And now, if the formula exists, we're going to see how to find those actual coefficients, the a, b, and c value. So we're going to take a look at this very first example, and in this special land that they've created of Connecticut, it was deemed that all cities must be built to join every other city directly by a straight road. Okay, so you can imagine in this first one we have city A, city B, city C, so we have 3 roads. Once we add the 4th city though, okay, we have 4 cities total here, then we actually add, and we have 1, 2, 3, 4, 5, 6 roads going on. Okay, so we have this nice set of data going on. All right, so every time we add a city, we're not adding the same number of roads each time. So what we need to do is we need to find out if we can figure a formula or a model to determine how many roads there will be if we know how many cities there are. Okay, so and the way we're going to start that is we're going to first determine whether, we're going to first determine the degree of the polynomial we'll use to model it. And we're going to use finite differences. So we're going to start here where we're going to do 6 minus 3. And we're going to do 10 minus 6, and we're going to do 15 minus 10, and we're going to do 21 minus 15. And you can see that in the first row, it's not constant, so it is not going to be a linear polynomial. Okay, so we have to continue on with our finite differences to see what our degree will actually be. If we do our subtractions here, 4 minus 3, 5 minus 4, and 6 minus 5, that gives us 1. That is in the second line of finite differences. So that means that we will have a polynomial that is a quadratic. So it will look like ax squared plus bx plus c. Okay? So now what we have to do is we have to figure out what that a value and that b value and that c value is. So we're going to set up a system of equations and solve that system. Now, what you're going to need is you're going to need the same number of equations as you have unknowns. We're unknown A and we're on unknown B and unknown C. So there's 3 unknowns. We're going to have to set up 3 equations. So we're going to use 3 of our points to set up those 3 equations. Okay? So the first one we're going to substitute in 3 for our x value. Okay, so that means I have a times 3 squared plus b times 3 plus c. Now that whole thing should equal my y value, which is 3. For my second equation, my y value is 6, and that should equal a times my x value of 4 squared plus my b with my x value of 4 plus my c. And the third equation I'm going to use, and I just picked these 3 because they're the smallest 3 sets of numbers. But my y value is 10, and that equals a times 5 squared plus b times 5 plus c. So the important step in this example is to, for one, find out what degree of your polynomial it is. So we found out it was quadratic, that the degree is equal to 2, okay? And we did that through finite differences. And then once we found that out, we know what our basic form of a quadratic is. And so we substituted in 3 sets of points because we had 3 unknowns. If this was going to be cubic, we would have 4 unknowns, so we would have to use 4 different sets of points. Okay?